So last time we learned the Newman projection. Okay. So here we first do a practice. Okay. Try to convert this wedge dash structure into Newman projection. Okay. Yeah, you guys try. Okay, practice on it. Okay. So that's one of the basic technique you have to learn in organic chemistry. Okay, convert the wedge dash structure to Newman projection. And probably next chapter we'll learn also how to convert a Newman projection, okay, back to a wedge dash structure, okay. Yeah. So wedge dash structure kind of pretty good. Show the whole stereochemistry of a molecule, okay. But Newman projection pretty good kind of for analyze the energy, okay, energy of the different conformations, okay, and those are pretty good to analyze some kind of reactions, okay. All right. So while you're working on this, okay. A couple of things, okay. First, I'm still greeting you guys here the quiz 3, okay. So hopefully, okay. So we'll be done by tomorrow, okay. And so another thing is about this week lab, okay. So make sure you sign up here the attendance the sign up sheet, okay. So online sign up sheet, okay. So 20 minutes, okay. And coming at you the sign up time, okay. So mainly just kind of take the melting point and also the mass of your caffeine, okay. And so when you take a melting point, a little bit different, okay, because the caffeine is easy to sublime, okay. So you have to use the flame to seal the end of your carbonate tube, okay. Once you pack your caffeine in, okay. And so lab instructor will show you how to do it, okay. Seal the end of the carbonate tube, okay. And because we use the open flame in the the instrument, okay. So in this case, when you clean up your vial, okay, so you go to another room, okay, so use the acetone clean it, okay. So the acetone and those the waste bottle in another room, okay. So you in the hood, okay, actually kind of in the hood or another room, okay. So your lab instructor will tell you where are they, okay. So just don't want kind of have some flammable solvent in the same room, okay. So if we use the open flame, okay. Yeah, okay. So if you have any question, you can still type in the chat window, okay. Right. So for the convert All right, someone want to try it, okay, that's fine, okay, yeah, go ahead. Yeah, someone want to try it, okay, so we can go ahead, okay. Yeah, for convert Newman projection, I mean the wedge dash structure to Newman projection, okay, so make sure you put your eye in the right direction and also draw the right position for all other bond, okay, so all the bond, okay. All right, so that's should be right, okay, good, okay. All right, good, okay. Okay, so relative pretty easy, okay, so normally speaking, kind of assuming that's your eye, okay, so you put your eye here and then that's your eye here, okay. You look through kind of these two carbons, okay. And then the front carbon will be kind of a single dot, okay, and the back carbon will be kind of the big circle, okay. All right, and then the front carbon, okay, so you have kind of bromide going down, okay, and then there are two hydrogen, okay, so this hydrogen, okay, so the point towards you actually kind of when you look at through this direction should be on your right, okay. Another hydrogen on your left, okay, so All right, and then for the back carbon, okay, so the bromide will be on the top, okay, so this hydrogen, okay, so with the wedge bond connected should be on your right, okay, and then dash bond, okay, so on your left, okay. All right, okay, so because the bromide has the bigger size, the much bigger size than the hydrogen, okay. So now we put these two large size substitute or kind of the atom, okay, 180 degrees, okay, to each other, okay. So this is the most stable conformation, okay, most stable, okay, because these two guys kind of far away to each other, okay. And this conformation we call the anti-conformation, okay. Okay. And then yeah, we can go ahead kind of rotated the for example, we rotated the back carbon, okay, we keep the front carbon same, okay, rotate back carbon, okay, like the 60-degree each time, okay. And then we generate kind of the second kind of conformation, okay. So the front carbon keep same, back carbon, right. So now yeah, if we rotate the 60 degrees, okay, so the bromine will overlap with the hydrogen here, and then there's another hydrogen overlaps with this bromine, and then the third hydrogen here. So this one we know that here from last time, okay. So this we call kind of eclipse, okay. So relative unstable, okay, higher energy, okay. Anti, okay. Anti means here these two are 180 degrees to each other, okay. So that means anti, okay. So kind of these two groups kind of on the totally opposite side, okay, totally opposite side, okay. So that's why I call anti, okay. Normally anti means kind of the two largest group, okay, two largest kind of subgroup, okay, on the individual carbon, okay, 180 degrees, okay, that's the anti, okay. Right, so that's eclipsed, okay. And this eclipse kind of not worse, okay. So although it's unstable, okay, but not the worst one, okay. So later we will learn the worst kind of most unstable one, okay. So yeah, for you guys, okay. So this is anti is kind of most stable one, okay. Right, and then next, okay, we continue and rotate it for 60 degrees, okay. And then we generate another staggered conformation, okay. Front carbon keep same. Right, back carbon, okay, so now the bromide here, and then hydrogens here, another hydrogens here, okay. So this one, yeah, looks like here similar to the anti, okay. So both are staggered, okay. But the two big group, okay. So two group, bromide kind of 60 degree to each other, okay. So they have little bit the instability, okay, little bit steric string, okay. So this conformation we call gauge, Gauche, okay, gauge, okay. So yeah, if we compare their kind of energy, okay, so this one should be higher than anti, okay. So yeah, you see some difference between anti and the gauge, okay. All right, and then we continue move the back carbon for 60 degrees, okay. We generate kind of the most unstable conformation. All right, BR here, okay, so 60 degrees, okay. BR here, hydrogen, okay. So this one is also eclipse, okay. So here eclipse, okay, label eclipse one. This is eclipse 2, but eclipse 2 is kind of much more unstable compared with the eclipse 1, okay, because the two largest group, okay, so just overlap to each other, okay. Too much kind of the torsional string, actually kind of maybe also some steric string, okay. All right, so this is we call it the most unstable, okay, maybe least stable, okay. So yeah. All right, and then you can go ahead kind of rotate another maybe just quickly show you guys, okay, 60 degrees, okay. And then we'll generate another gauge conformation. AOCHE, okay. So these two actually kind of same stability, okay, same stability, okay, these two, okay. And then you can continue, okay, all right. And then we can draw their energy, okay, stability with their different conformation, okay, on the this we call the dihedral angle, and also the energy, okay, so diagram, okay. You can see anti is the most stable one, okay, because the two big group, okay, 180 degrees from each other's, okay. And then we continue rotate, okay, so we will generate kind of eclipse 1, okay. So that's unstable, okay, but not worst, okay. And then we rotate another 60 degrees, okay, and then we generate a gauge conformation, okay. And then if we further kind of rotate kind of back carbon, okay, so that's give kind of most unstable conformation, okay. So the two big group overlap to each other's, okay, and then that's the least stable one, okay. And then you can continue this process, okay. All right, for you guys, okay, so just yeah, first, yeah, you need to know how to convert the wedge structure into the Newman projection. Second, okay, so yeah, you should be able to analyze the kind of the different conformation kind of. Yeah. Gauges belongs to a staggered, okay, so yeah. This one we call kind of staggered, okay. This one also called staggered, okay. And this one actually anti also belongs kind of staggered, okay. Yeah, that's right, okay. And so yeah, you should able to kind of analyze their energy stability, okay. Most common question kind of for Newman projection is I give you one kind of the wedge structure, okay. Ask kind of draw more stable Newman projection and also the least stable kind of the Newman projection, okay. So yeah, you don't need to draw all of them kind of for example, for this one, okay, you need the least stable one should be this one, most stable one you draw me this one. That's it, okay. So we'll do some practice here in the maybe discussion tomorrow. Okay, so yeah, you'll see kind of what kind of types question you'll see in the probably quiz 4 and also exam 2. Okay, about yes, well, about Newman projection. Okay. All right, good. Okay, yeah. If you have any question, just type in chat window. Okay. Okay, so next kind of we switch to another topic called the conformation of your cyclic arcing, okay, cyclic structure. Okay, so for cyclic arcing, depends on how many carbon in the ring. Okay, so they have different ring string. Okay, so ring string actually kind of has the following two components. Actually, kind of we have a little bit summary. Okay, so far the string we learned is first called the steric string. Okay, the first string we learned is steric string. Stack string kind of the two section group, okay, too close to each other, okay. So yeah, you have some kind of very big group, okay. So yeah, another big group, okay, very close to each other, okay. You generate kind of the string, okay. Right, so that's what we call staggered string, okay. And then yeah, the second string we learned in the class last time we called it the torsional string. So torsional string happened if in one conformation is in the eclipse, okay. Conformation, okay, and then the front bound and also back bound kind of the overlap to each other, okay. For example, that's the eclipse. This is also eclipsed, okay. And then you join kind of string we call the torsional string, okay. For cyclic the arcing, okay, so arcing, okay, so the string we call the ring string, okay. Ring string has the two components, okay. The first one is the angle string, okay. So angle string is because of the a certain number of ring, okay. So yeah, you cannot reach the 109.5 degree bound angle, okay, because of the suppose all the carbon on the cyclic arcing should be tetrahedron. The idea the bound angle should be 109.5, okay, but sometimes you cannot reach 109.5, okay, too less kind of the larger than kind of 109.5, okay. So that's you generate the ring string. A second kind of the torsional string, okay. Torsional string in certain conformation, okay. So yeah, you cannot make all the bond kind of in the staggered conformation, and they have to be in the eclipse the structure conformation, okay. So then you generate kind of a torsional string, okay. So yeah, that's the two, okay. And then here the chart showed you the different ring size and also the different ring string, okay. And so yeah, for example, 3 membrane, 4 membrane, 5, 6, 7, 8, 9, okay. So if you take close look, you find a 7 membrane cyclobutane, huge kind of ring string, okay. So 26.7, okay. And then cyclobutane, okay, 4 membrane ring string is also quite huge, okay. But yeah, when the ring size increase to 5 carbons, okay. So yeah, the ring string is much less, okay. So yeah, it's kind of only 6.5, okay. The miracle happened, okay. So yeah, that's right, okay. So yeah, when we talk about kind of the staggered conformation, always the more stable than the eclipse, okay. But the more stable one is the anti, okay. Anti is more stable. Right, and then when we come to kind of 6 membrane cyclohexene, okay, so there's no string case, so no ring string case, totally 0, okay. So that's a pretty interesting case, okay. But if we further increase the ring size, okay, so 7 membrane, 8 membrane, 9 membrane, and then little bit increase the ring string, okay. Right, so here we'll study all these the ring size kind of under ring string, okay, and mainly focused on the 6 membrane case, cyclohexene, okay. Right, we do one by one, okay. And the first one is cyclopentene, okay. Cyclopentene only 3 members, 3 carbons, okay. And this guy, okay, so we have very strong kind of a huge angle string, okay. Because this is a triangle. Triangle, no, we know that kind of bond angle should be 60 degrees, okay. That's far away from 109.5, okay. So this carbon is supposed to be kind of a tetrahedron, but you force it into kind of only 60 degrees, okay. So that's the huge the angle string, okay. And so also there the very significant of the torsional string, okay, torsional string for the cyclopentene, okay, because these 3 carbons, okay, so in the planar structure, okay, the force this CH bond, okay, in the eclipse, okay, you see kind of eclipse overlap to each other, okay, so that's a huge torsional string, and then overall, okay, so cyclopentene has a huge ring string, okay, both the huge kind of torsion string and also angle string. Okay. All right, okay, so for cyclobutene, okay, so if we increase the one carbon, okay, so should be kind of something like a square, okay. If it's planar structure, okay, so square we know that the bond angle should be 90 degrees, okay. But for the reality, okay, so the cyclobutene not planar structure, okay. So little bit pocket, okay, so like kind of a little bit folded, okay. And the reason for that kind of if it's in the square I mean the planar structure, okay, so there will be huge torsional string, okay. So all the CH bond, okay, can see clearly, okay, kind of eclipse to each other, okay. Eclipse case, so the torsional string too big. And then if we cyclobutene little bit folded up, okay, and will greatly release the torsional string, okay. So we can see here, okay, so little bit packed, okay, it's a little bit kind of staggered, okay, for the CH bond, okay. Staggered, okay. So that's release the torsional string, okay. But problems kind of once you little bit folded the cyclobutene, okay, so we'll further decrease the bond angle, okay. So now the bond angle not 90 degree anymore, okay, become 88, okay. So that means you increase the angle string, okay, but because you release a significant amount of torsional string, okay, overall, okay, so it's more stable, okay. So if you cyclobutene in kind of this we call the Parker conformation, okay. So release the torsional string, but get more angle string, okay. Overall kind of more stable, okay. All right, and if we further increase the kind of ring size, okay, so to 5 membrane cyclopentene, okay. So if it's kind of a ring structure, okay, so planar structure, okay, so the bond angle should be 108, okay, so that's very close to 109.5, okay. So that means cyclopentene shouldn't have too much angle string, okay. And for reality, okay, so cyclopentene is also not a planar structure, okay. So there's a 1 carbon, okay, so just a little bit bended up, okay. Bended up out of the plane from other 4 carbons, okay. So why is that, okay? Because if the cyclopentene is in a planar structure, okay, so there will be huge kind of torsional string, okay. So you can see all the kind of CH bond, okay, eclipsed, okay. So that's the eclipse torsional string, okay. And too much torsion string, okay, so cyclobutene don't want that, okay, so that's try to release this torsion string, okay. So in this case the 1 carbon will little bit folded up, okay, and then that's you can put this CH bond into the staggered conformation, okay, greatly release the torsional string, okay. And this conformation we call the envelope kind of conformation, okay. Envelope, okay, so everyone maybe you guys kind of don't write the letters anymore, okay. So that's some envelope, okay. So the folded up, okay. So that's what I call kind of envelope, okay. All right, okay, so yeah, so if you bonded kind of one carbon up, okay, so the bond angle kind of still close to 108, okay, and so that means here the cyclopenting case not too much angle strain, okay, and but here the torsion string is greatly released, okay, so yeah, if you need to be folded up, okay, so yeah. So yeah, that's just for you guys. Just keep in mind, okay. So yeah, cyclopenting is not planar structure, and in this kind of envelope conformations, okay. All right, okay. So now we move to a most interesting the cycloarcing, okay. So cyclohexene, okay. So cyclohexene is similar to other the cyclopenting, cyclobutene, okay. Also note a planar structure, okay. So note the kind of hexene, okay. And so it's in this kind of we call it a chair conformation, okay. So yeah, little bit folded, okay. So yeah, and so overall structure looks like a beach chair, okay. Beach chair, okay. So you can see kind of this chair back where you can put your feet on, okay. So that's kind of folded because that's why we call it now chair conformation, okay. And then interesting for cyclohexene case, so there's no angle string and also no torsion string case. So because the first case, so for the old carbon case, so here, okay, all are in tetrahedral structures, okay, and then 109.5 degrees bond angle case. So okay, actually now close to 109.5, okay. So that means there are no angle string, okay. And also, okay, so if you look at it, it's Newman projection for cyclohexene, okay, so we actually kind of look at it from this direction, okay, so these two, okay, are bridged carbon, okay, so that's bridged carbon, okay, and then you will find kind of all the CH bond, okay, are staggered, okay, all CH bond are staggered, and then that's greatly release all the torsional string, okay, and then the whole molecule has no string, okay, so that's pretty nice, okay, so very stable, okay, string free, okay. All right, and so here comes kind of important thing, okay, so when you take close look of the cyclohexene, okay, so you find that there are H, okay, hydrogen, okay, so in kind of a little bit different arrangement, okay, 6 hydrogen kind of relative perpendicular to this carbon ring, okay, relative kind of straight up, straight down, okay. So these 6 hydrogen we call it the axial, okay, hydrogen, okay. And if you take another look, okay, so this red hydrogen, okay. So this red hydrogen, okay, we call the axial hydrogen, okay. 3 red hydrogen kind of going up, okay, and then 3 red hydrogen are going down, okay. And then another 6 hydrogen, okay. So this blue one, okay, and so we call it equatorial, okay. So those hydrogen somehow kind of extend out of the cyclohexene ring, okay, and so looks like on the equator of the whole molecule, equator, okay. So that's why we call it the equatorial bond, okay, equatorial hydrogens, okay. And if you take second look of this 6 the equatorial hydrogen, okay, so you find kind of this one, and this one, 3 going up, okay, and then this, and this, okay, 3 hydrogen going down, okay. And so if we compare the equatorial hydrogen and also axial hydrogen, okay, so equatorial hydrogen kind of the more stable, okay, because equatorial hydrogen kind of extend out, okay, from the ring system, okay, there's no the stereo hindrance, okay, and axial hydrogen kind of a little bit too close to each other, okay, so that's actually later we'll learn that called kind of the 1,3 diaxial the interactions, okay, and so. Okay, yeah. So for both equatorial and axial, okay, they have kind of 3 going up, 3 going down, okay, both equatorial and axial, okay. So the red are axial, okay, okay, and then you can see kind of 3 red going up, 3 red going down, okay. And then for the equatorial bond, okay, also 3 going up, 3 going down, okay. You can see this one, and this one, okay. So that's going up, okay. And this one, and this one going down, okay. 3 equatorial going up, 3 going down, okay. And then for the axial, same thing, 3 going up, 3 going down, okay. So later we will learn how to draw it, okay. So don't worry about it, okay. Right. So that's so far you guys just keep in mind, okay. So for each bond, okay, there are two property, okay? Each bond two property, okay? One is kind of equatorial or axial, one is kind of going up, going down, okay? So those here just keep in mind, okay? Yeah. And if you look at individual carbons, okay, so carbon, okay, so you find that each carbon, okay, attach one axial bond and also one equatorial bond, okay, one axial hydrogen, one equatorial hydrogen, okay. So if we see the equatorial hydrogens, okay, going up, okay, so for example in this case, okay, and axial hydrogen, okay, will going down, okay, vice versa, okay. So yeah, if we have the axial kind of going up, okay, and then equatorial will going down, okay. So that means on each carbon, okay, so also keep in mind, okay, one equatorial, one axial, okay, and then one will be going down, one will be going, another one has to be going up, okay. All right, so to help you guys kind of has a little bit better view, okay. So yeah, here's kind of the three-dimensional model, okay. So generic from Chem 3D, okay. So I think that's maybe better than kind of make the handmade model, okay. Right, so that's the cyclohexene, okay. So you can see clearly, okay. So this the carbon in kind of we call the chair conformations, okay. And then you see kind of three kind of axial bond, okay, point up, okay, and then another three axial bond kind of point down, okay. So that's straight going up and going down, okay. And then if you take a look, okay, so that's better view, okay. So you see kind of all six kind of equatorial bond extend out away from the ring, okay. But here the three going up, okay, this one, this one, this one, okay, and then three going down, this one, and those this one, okay. So when you put it like this, okay, maybe a little bit angle. Yeah, that's here the chair conformation, okay. Okay, so one of the most important technique you have to learn in organic chemistry is know how to draw the chair conformation of your cyclohexene. Actually, kind of in future case, so if you want to determine whether one people has taken the organic chemistry or not, okay, so just ask him to draw the chair conformation of cyclohexene, okay. So if he cannot know how to do it, okay, that means probably they didn't take the organic chemistry or kind of didn't do well in organic chemistry, okay. That's the fundamental technique, okay. All right, so take out your pen and also get a kind of the paper, okay. So learn together with me, okay. So that's the basic fundamental technique you have to learn in organic chemistry, okay. All right, ready? Okay, let's roll. Okay, so the first step is you need to draw the carbon framework, okay. So you first need to draw two parallel lines, okay. So like this, okay. So these two parallel little bit mismatch, okay, each other's, okay. And then this line, okay. So somehow like the 30 degree, okay, 30 degree from kind of the y-axis, x-axis, okay, 30 degree, okay. Okay, and then next case, so you need kind of that's the carbon, 4 carbons, okay. Next case, we need to put another 2 carbon on, okay. So you need first to find the one spot, okay. Pretty much same distance, okay, to this the 2 end, okay. It's 2 end, okay. So and then you kind of link them together. All right, okay. Okay, following thing, okay, we draw the kind of another the bond, okay. So another thing, okay, so similar maybe. Same distance to another end of this 2 parallel line, okay. Yeah, so that's the carbon framework, okay. So you can get it, okay. Okay, so now we move to kind of important step, okay. So try to add the hydrants, okay. So we'll add the axial hydrant first, okay. So the straight up, straight down one, okay. But we already know that kind of the 3 axial hydrogen should be kind of going up, 3 axial hydrogen should be going down, okay. So how do we know which one going up, which one going down, okay? So we need to look at carbons, okay, carbons, okay. All right, so quickly you find kind of 3 carbons, okay. So going up, okay. So these 3 guys, okay, that's kind of up, okay. and then 3 carbons kind of going down. Okay, this one, and this one. All right. Okay. So for the carbon going up, okay. So yeah, the axial bond will be going up. Okay. So yeah. Yeah, just go straight kind of draw the hydrogen bond, the hydrogen kind of the CH bond. Okay. And then for the carbon, okay, going down, okay, so this 3 carbon okay, going down, okay, and then its axial bond will going down, okay, so like this. Yeah. So that's we down the axial bond, okay. Okay. So again, okay, so which carbon is CH bond going up, going down, okay, depending on which carbon, okay, so you attach, okay, so a carbon is up, okay, that's going up, okay, and the carbon down, the carbon with hydrogen CH bond will going down, okay. All right, so next, we need to touch the equatorial bond, okay. So equatorial bond, we just learned in the previous slide, okay. So for each carbon, okay, so there's one equatorial bond, one axial bond, okay. So if the equatorial bond kind of equal, if the axial bond going down, okay, equatorial bond should be going up, okay. So if axial bond kind of going up, okay, equatorial bond should be going down, okay. So that's they have an opposite directions, okay, opposite kind of pointing, okay. What's that mean? Okay, so you can here. So this carbon has the axial hydrogen kind of going down, okay. So that means its equatorial bond, the equatorial hydrogen should going up, okay. So how do we draw the up kind of equatorial bond, okay? So you need to find its a parallel kind of bond in the molecule, okay. So that's actually this guy. These two are parallel to each other, okay. Okay, and then similar thing, okay, we move to this carbon, okay. So this one already has axial bond going up, okay, equatorial bond should going down, okay. So how do we draw equatorial bond, okay? So we need to find a kind of parallel bond, actually this guy. So these two parallel to each other, okay. Right, and then similar thing, okay, for this carbon, okay, so axial bond, okay, going up, equatorial bond should going down, okay, so going down, okay, so this parallel to here, okay. And then we can go ahead and draw the more kind of equatorial bond, okay. So this one, axial bond going down, equatorial bond should going up, okay. So this bond actually parallel to here, okay. Similar thing, okay. So this one, axial bond going down, equatorial bond should going up, okay, and then going up, okay. Right. This line parallel to here, okay. And in the end, okay, so this hydrogen, okay, this carbon has kind of axial going up, equatorial bond should going down, okay. Going down, okay, so that's should be this direction, and then parallel to this line, okay. So that's you can draw very beautiful kind of the cyclohexene, okay. So after that you follow the rule, okay. So should be easy to draw it, okay. But unfortunately, each year, okay, so we always have some student kind of difficulty to draw kind of the chair conformation of cyclohexene, okay. Just keep in mind, okay, you do it stepwise, okay. So draw 2 parallel lines and then draw kind of connect all the things, okay. Journey kind of this chair conformation by carbon framework. Most important kind of the connect kind of the axial bond first, 3 going up, 3 going down, okay, and then add the equatorial bond in, okay. So if equatorial bond going, if axial bond going down, okay, and then equatorial bond should going up, okay. If axial bond kind of going up, equatorial bond should going down, okay. So those if you follow this step, okay, so that will be kind of you want to miss that, okay. For the middle axial H going down. It's going down. It's just point down, okay. So that's like this. Yeah. On the right. So I guess some student kind of said maybe we pull this bond going here, okay. So normally you need try to kind of find its parallel line, okay. So that's normally kind of the 2 bond away, okay. So draw like this, okay. So don't worry, okay. So we'll practice a little bit more in the discussion tomorrow, okay. So that's fundamental technique, okay. All right. So why we need to care about kind of draw the chair conformation, okay? Because for individual cyclohexene, okay, they have more than 1 chair conformation. There's kind of 2 chair conformation, okay. So those we call the ring flip, okay, ring flip, okay. So what's that mean, okay? So here kind of the cyclohexene, okay. So this one only highlighted hydrogen on the first carbon and also first carbon and also carbon 4 and carbon 1. Okay. Okay, so yeah, when you do ring flip, okay, what happened kind of the original carbon going up will going down. Okay, original carbon going down will going up. Okay, so you see kind of the 2, 4, 6. Okay, those carbon should be kind of going up in the ring flip structure, and then when you do ring flip structure, okay, and then 2, 4, 6 going down. Okay, and if the origin kind of going down, okay, 1, 3, 5. Okay, so now kind of going up. Okay. And because this up-down change, okay, so fundamentally changing the all the hydrogen attached to all the individual carbons, okay. So yeah, you see here, okay. So after reflip, okay, so for the carbon 4, okay, So original equatorial bond, equatorial hydrogen, okay, this blue one, okay, become kind of axial, okay, and original kind of axial hydrogen become equatorial, okay. Same thing here, okay, for the 2 hydrogen on the carbon 4, original the equatorial become axial, axial become equatorial. Okay, so that means kind of the ring flip convert axial hydrogen to equatorial and then equatorial to hydrogen axial. Okay, but one thing keep in mind. Okay, so yeah, equatorial axial can change. Okay, but yeah, they want to change the pointing. Okay, pointing. If it's going up, still up. If down, still down. Okay, so here you see still the hydrogen on the carbon 1 and carbon 4. Okay, so for this red one. Okay, so yeah. Once you do reflip, okay, it's still point up. Okay, see here, it's still up. Okay, so for the blue one, okay, so although change to kind of equatorial to axial, okay, still point down. Okay, and same thing for the 2 hydrogen on the carbon 1, up, still up, down, still down. Okay, so that's keep in mind. Okay, so yeah, when you do reflip, okay, only change kind of equatorial to axial, axial to equatorial. Okay, a pointing won't change. Okay, pointing won't change. Okay. All right, so here come kind of the most difficult thing. Okay, how do we draw the reflipped structure? How do we draw reflipped structure? Okay, so a lot of students kind of get confused. Okay, and then yeah. All right, so again, take out your pencil and those get the paper. Okay, so here draw you how to kind of draw reflipped one. Okay. Right. So first, yeah, you need to draw the basic carbon framework for one kind of chair conformation. Okay. Yeah, this is one. Okay, so yeah, draw it. Okay, and then second. Okay, so yeah, you just take a mirror imaging of this structure. Okay, take a mirror image. Okay, right. What's that mean? Okay, you just assuming there's kind of mirror. Okay, in the middle. Okay, and then you just kind of reflect. Okay, right. Mirror imaging. Okay, so that's should like this. Okay. Okay, so that's it's a mirror imaging. Okay. Okay. So this carbon is mirror here, this carbon mirror here, this carbon mirror here, and this carbon mirror here, and then here, and then this one here. Okay, so that's the step number 1. Okay, so yeah, reflipped. Okay, all right, and then step number 2. Okay, so yeah, you need to number the carbons. Okay, so when you number the carbon, okay, you don't do the mirror imaging. You have to go the same direction, same kind of same positions. Okay. Right, what's that mean? Okay, so we do it one by one. Okay, so assuming we start with this carbon. Okay, so we do the clockwise. Okay, 1, 2, 3, 4, 5, 6. Okay, so sorry, it's kind of here. Okay, all right. So if you want to number another kind of it's mirror image. Okay, so you do the same thing. Okay, same way. Okay, so yeah, the number don't do mirror image. Okay, so that's your carbon 1. Okay, 1, 2, 3, 4, 5, and 6. Okay, so we still do kind of the clockwise. Okay, right? That's key thing. Okay, so the base carbon framework. Okay, so you do kind of mirror image. Okay, but the number you do the same way. Okay, same direction. Okay, same kind of starting point. Okay. Okay, so once you get these two right. Okay, so the following kind of should be relatively easy. Okay. So yeah, we just do the same thing at the equatorial bond, axial bond first. Okay, so yeah, the axial bond. Okay, depends carbon point up, point down. Okay, so yeah, these two carbon, these 3. Okay, so point up. Okay, so that should be kind of equatorial bond should going up. These 3 going down. Okay. Yeah, and same thing. Okay, so yeah, we add the equal to axial bond first, okay? So if the carbon kind of point up, okay, and then the hydrogen kind of also going up, okay? Carbon going down, hydrogen also going down. Okay. All right, and next kind of you can add the axial bond, okay, equatorial bond, okay, sorry. Equatorial bond, okay, so just keep in mind, okay, if the axial bond point down, okay, equatorial bond should point up, okay. So this line parallel to here, okay, and then equatorial bond, okay, here, okay, so here parallel to here, okay. All right, so you go ahead and add all the hydrants, okay. Okay. Okay, and then falling case, so we can do another one, okay. So same thing, okay. So yeah, just going down is going down, okay. Going up is going up. Going up is going up. Going down is going down. Going up. Yeah. Right. So for you guys, yeah, probably take some time kind of learn how to draw the mirror image in case but overall rule, okay, so at last you know how to do it, okay, so do it step by step, okay, you won't miss it, okay. All right, so just carbon framework, you do kind of the mirror imaging, and then numbering the carbon should kind of do the same thing, okay, and then falling at the equatorial bond and the axial bond, okay. And so why we kind of care about this much, okay? So because these two structures looks like very similar, okay? The reason for that, later this chapter we'll learn how to draw the kind of substitute cyclohexene. Substitute cyclohexene means kind of one of the hydrogen, maybe two or maybe three, okay? We'll replace by substitute group, okay? And then this substitute group can be in equatorial or be axial, okay? So then you have to do reflip, okay? And draw the both structures, okay? So to determine which one is more stable, okay? I will give you guys kind of example later, okay? So just keep in mind, okay, this is kind of the important technique you have to learn, okay? So first, know how to draw the chair conformation, add the equatorial bond, and then also the axial bond. Second, kind of know how to do reflip, okay? And draw is kind of the corresponding structure, okay? Okay, so here's kind of a small movie, okay? Show you guys how to kind of how to kind of reflip happened, okay? So just see. All right, so very beginning you see kind of the three hydrogen axial, okay, and then red one is kind of the equatorial, okay. But once reflip, okay, so you see kind of the red one become kind of the axial, and then blue one become equatorial, okay. Maybe stop here, okay. So when you do the reflip structures, okay, so the actually kind of the molecule will bypass some other the conformation, okay. So one conformation we call the bolt, okay, just like the bolt, okay. And then another conformation we call the twist bolt, okay. Yeah, that's twist bolt, okay. And then you can do the reflip, okay. Right, so now the reflip again, okay, you can see, okay. So the three blue hydrogen, okay, so become kind of axial, okay. Right, and then they kind of do the reflip again, okay. So generate kind of a chair conformation, half chair, okay. And then now new chair conformation, okay. So the red hydrogen become the axial, okay, and then blue one become equatorial, okay. So now we do it again, okay. So the bolt, twist bolt, okay, and eventually, okay. So the new chair conformation, okay. So the blue hydrogen become axial, and then the red one become equatorial, okay. So externality of the ring, okay. Yeah, now it's kind of do the final round, okay. So if in the class, okay, so I may show you guys kind of real cyclohexene model, okay, and show you how to do kind of reflip, okay. But it's kind of the online class, okay, not easy kind of just the hard to see, okay. So yeah, that's it, okay. All right, okay, and then for you guys, okay, so you can see, okay, put this page away. So in addition to the chair conformation, okay, so for cyclohexene, there are also some kind of conformation, okay? So yeah, one we call the bolt, okay, and another one called twist bolt, okay, and then last one kind of a half bolt, okay. So yeah, normally when you do reflip, okay, change one chair conformation to another chair conformation, you will bypass all these the conformation, okay. Normally kind of you first kind of bend one carbon up, okay, then kind of half chair conformation. This one's kind of extremely unstable, okay. And then you further twist the atoms, okay, so carbon, okay, then twist bolt conformation. Twist bolt conformation relatively stable, okay, because the hydrogen is in the staggered conformation, okay. And then you have to bypass the bolt conformation, okay. So bolt conformation kind of not stable as the twist bolt, okay, because there's hydrogen in the torsional the kind of eclipse structure, okay. So no stable, okay. And then you go to kind of another twist, okay, eventually another half chair, and then give kind of the reflip the chair conformation, okay. And here you don't need to know how to draw the other conformation. You only need to know how to draw the chair conformation to reflip. That's it, okay. And the only thing you need to memorize kind of their energy and also the stability, okay. The most stable one should be kind of chair conformation, okay. Write it down, okay. And then followed by twist bolt, conformation, okay. And then followed by bolt conformation. And least stable one is half chair, okay. Right, so that's it. As long as you know there kind of energy ranking, that's enough, okay. So maybe I will in kind of the quiz 4 or maybe exam 2, okay. I will test you guys kind of maybe run one ranking question, okay. Ask kind of rank their kind of stability or kind of energy, okay. So for this 4 conformations, okay. All right, okay. So come here, okay. So we already learned kind of the 3, 5, 6 membrane kind of conformations, okay. If we further increase the ring size, okay, so for example here the 7 membrane, 8 membrane, or more 9, 10 membrane, okay, so all this kind of large ring, okay, so also note here the planar structure, okay, so pretty much kind of folded, okay. And because they cannot reach ideal kind of 109.5 degrees bound angle, okay, and also sometimes kind of the torsional string due to kind of eclipse structures, okay. So for the big ring size, okay, more or less they have a little bit of ring string, okay. So not too big, but little bit, okay. And especially for the some bigger ring size, okay, like cyclooctane, okay. So the 2 hydrogen sometimes kind of have to point inside of the ring, okay. And then you generate some kind of we call it the transannular string, okay, also called a cross ring string, okay. Cross ring string actually kind of also belong to the steric string, okay. Yeah, that's belong to stacker string. Stacker string, okay, so remember we learned before kind of the 2 group or kind of 2 atom force too close to each other, okay, and then that's your general string, okay. So so those please keep in mind, okay. All right, okay. So here we come to kind of the important case also kind of the critical thinking. Why we care about kind of the rinse flip, okay? Why need to know how to draw the chair conformation, okay? Because we have to analyze the different kind of the substitute cyclohexane, okay, their stabilities, okay. And for example, okay, so for mono substitute cyclohexane, okay, so this is kind of methyl cyclohexane. There's kind of methyl group replace 1 hydrogen, okay. So this one can also have the 2 chair conformations, okay. Right. So to reflip, okay, so very beginning, okay, so for the last one, okay, so you can put the methyl group at equatorial positions, okay. And then for the right one, after you do the reflip, keep in mind, okay, axial become equatorial, okay, equatorial become axial, okay. So now the methyl group in the axial positions, okay. So if it's in axial positions, okay, so it's kind of last stable, okay, because there's the 1,3 diaxial interactions, okay, too close to the 2 axial hydrants, okay, and then there are kind of a little bit steric hindrance, okay. But if you for the left here the chair conformation, okay, so reflip structure, okay, so the methyl group is in equatorial position. Equatorial kind of we already saw kind of model, okay, so extend out of the ring, okay, so that's actually kind of a pretty good model here, okay. The no interaction with any of the atom in the cyclohexene, okay, so that is more stable, okay. So that's why when you do ring flip structures, okay, so this the conformation kind of more stable, okay, so that's 95% of the time, okay, so the methyl cyclohexene will exist in this conformation, okay? Only 5% okay methyl in the axial positions, okay. All right, okay, so it's already 1:50, okay, so we'll stop the class here today, okay, so and in the discussion tomorrow, okay, we will try to study kind of draw the chair conformation for cyclohexene, okay. And also pretty much we are also done the chapter 6, okay, so need to be the leftover for the Friday, okay, so maybe this afternoon, okay, so I will give you guys kind of the chapter 6 homework assignment, okay. All right, any questions? All right. So I have office hour from 3 to 5, okay, so if you guys have any questions, okay, so you can come back ask me, okay. And otherwise, okay, have a good day, everyone.